Hey, this is Leach with Simpson Math, and before I get started, I am in a little bit of darkness, a little bit of issue with the upper light, so to move in some other light so I'm not, wouldn't be in a complete cave dark situation, so we'll make do. But in this video we're going to be talking about standard deviation. I'm going to do a little bit of a mini teach just to help you understand what in the world standard deviation is, what is it that you're finding whenever you might put into a calculator and it spits out. And then I'm going to go through 3 technology options for finding standard deviation. I'll show you how to find it on a TI-84 or similar calculator, then in Desmos, and then lastly in Excel. So let's get started with talking about what in the world is standard deviation. Well, there's a little bit of vocabulary that we need to break down here. So first up, here's just a made-up data set. It's 1, 2, 2, 3, 5, 6, 6, 7. It's, as I say, a little bit academically sterile. It's just a nice, clean example that I've judiciously chosen for some reasons. We have some duplicated numbers, so forth. So first, we're learning about this thing called standard deviation. So what in the world is a deviation? Well, first, a deviation is the distance and direction that a specific data value is away from the mean. So if you take a look at this data set, and I have it graphed over here, you can see that the mean is clearly at 4. The data set would balance nicely at 4. There's a stack, equal size stack actually on either side. You could do the math. You can add them all up, divide by 8, and you would get 4 for this sample mean. I'm assuming that this is a sample from a larger population right now. So if I was to grab the number 6, one of my 6s, I would notice that the deviation, well, first its distance, I said its distance and direction. Its distance is 2 units from 4, 2 units from that mean. And it's also greater than that 4, so I'm going to imply greater as, I'm going to signify that it's greater as being positive. So the deviation for 6 is 2. But what about 1? Well, 1, it's 3 units from 4, so if I was stating at 4, I would go 1, 2, 3 units. And it is less than 4, but to signify that it's less than or to the left, let's use its direction here. So we're going to say that its deviation is -3. So I could do that same thing and get the deviations for all of those. But first, some of your formula folks, and so if you needed a formula for deviation, it's just simply x minus x bar. Think about that word deviation, make sure that makes sense. Think about a similar word in other contexts, like you might deviate from a path. At my school at Temple College, from our math building to a common parking lot, the sidewalk kind of does a little bit of a wiggle. And so a lot of times students don't walk on the sidewalk because it's like, why go through the wiggle? I'm just going to go straight to my car. And so they deviate from the path. The path is where they're expected to be, and they deviate from that. So if I take a snapshot of them, they should be here, but they actually end up here. I could take a snapshot and find that distance. They might be to the left, might be to the right, and so I could see that distance and also direction. Are they to the left or are they to the right of where they're supposed to be? That you deviate, or in this case it's a deviation. Casually, I like to think of deviation as just observed as expected, or throughout the course I often think of this as just O minus E, or observed obs minus exp, observed as expected O minus E. This is a very, very, very important concept throughout this course. The crux of statistics is this. I saw this value, I was expecting this value, I didn't get what I was expecting. Was that weird? That's kind of the gist of what this course is about. So we're learning about this thing called a standard deviation. So standard deviation, I should have said earlier, if you're learning it and trying to figure out what it is, it's one of the measurements of spread. So we learned about range or the IQR. Those are measurements of width, of how wide the data set is. With the standard deviation, we want to find a little bit more nuanced data value, and a little bit more nuanced statistic or measurement. One that takes in all the data values, and not just the biggest and the smallest. So it takes in all those data values and use it to give a more complete measurement of spread. And so we're looking at all the deviations, and we're finding, notice that's the first word in standard deviation is standard. So if I was to have you think of a words or concepts like standard in our English language, a lot of students think of the usual, the typical, the expectant, the regular thing. It's the standard way of doing things, the standard, the typical way. standard operating procedure. That standard is the basic, baseline, regular thing that we expect. So it's the regular, basic, not basic, but the regular deviation, the typical deviation that we're expecting. So let's build up to that concept. So if I take a look at this, again we have our data values. Let's take a look at these deviations here. So we said that 6 has a deviation of 2, 1 has a deviation of -3. If I continue that process for all of them, I see I can get these -2 deviations, these 2 deviations. This one has a deviation of 3. This one has a deviation of -1. So I'm trying to ultimately basically find more or less the average deviation, the typical, the usual, the regular, the average deviation. So let's go ahead and try to average this. So if I try to average these deviations, look what happens. Well, 1 plus -1, that's 0. 2 plus -2, those are 0. 3 plus -3, that's 0. So that's not going very well for me in this average department, because the range of this is 6, the IQR of this is 4. There's clearly some variability. The data values are wiggling. They're not just all 4. In fact, none of them are 4. There is a clear amount of variability. I should not just have a 0 standard deviation or measurement of all these, a summary of all these deviations. I mean, 0 wasn't even one of them, or even close. So we need to fix that. So just my deviation by itself, x minus x bar, not good enough. What if I drop the whole distance part? Drop the whole direction part and just look at the distance. So if I look at the distance that these values are away from the mean, notice what I've done here is I've gotten rid of the negatives. Put on a little chapstick, sorry. I've gotten rid of the negatives. Mathematically, that is finding the absolute value. So you see, what we've done is we found the absolute value of those deviations, and we've gotten this. So instead of -1, it's 1. Instead of -2s, it's 2. Instead of -3, it's 3. But notice if I have the absolute value of 1, it's still just 1. It doesn't change signs. So these are the distances that the values are away from the mean. So I have these distances now. So let's find the average distance, specifically the average distance that the values are away from the mean. So I take all these distances, add them up, and I end up with 16. And let's average them. I see 8 numbers. So 16 divided by 8 is 2. And visually that should make sense. That that the average distance that these values are away from the mean is 2. Well, I mean, heck, half of them are exactly 2 units away from the mean. This one's only 1, but then these ones over here kind of compensate and are 1 extra 1 away at 3. So yeah, that average distance that the values are away from the mean does make sense to be 2. We actually have a specific measurement for this. It's not that big of a deal. You don't need to, at least if you're in my classes, you don't need to hardcore learn this. But I really like it, just to at least point it out here, because if you can understand this conceptually, then the standard deviation should then make a lot more sense. So it's actually called the mean absolute deviation. If you look at the math that we did here, we found a deviation, then we absolute valued the deviations, and then we found the mean of those absolute deviations. So that's why we call it the mean absolute deviation. I do want to go ahead and get into talking about this formula, because you'll see the formula for the standard deviation in just a second, and I want this process to make sense here. So this is the formula for that mean absolute deviation. So here's how it works. So notice we first found the deviations of all of our values. Then we absolute valued, so now I have it around absolute values bars. And then to find the mean, I need to add them all up, and the add them all up part is this symbol. Oh, I have it written down later, but that is a capital sigma. I'll write that later, but it's a capital sigma. Capital sigma in math just means add up what you have. So add up all of these pieces. So I would add up 3 plus 2 plus 2 plus 1 plus 1 plus 2 plus 2 plus 3, and we get the 16. And then this n is the sample size. So throughout this course, you'll see that often. N is often your sample size. So I had 8 things. So it's the sum of all of my absolute deviations divided by n. And that's what I got that's how I got the average distance. Now the standard deviation, like I said, the standard is the typical, the usual thing. So the standard deviation is the typical, usual deviation. So if I had to define this, I would call it this. The standard deviation is the typical distance that the values are, and the values in a data set are away from the mean. Notice it is not the average distance. It is almost, it's going to be very, very, very close to the average distance. This is the actual average distance the values are away from the mean. The average when we're talking about mean. So this isn't quite an average. My standard deviations I'm going to find are going to be just a little bit bigger than this. And that has to do with, because we're about to be squaring this instead of absolute valuing. And if you think about your Pythagorean theorem experience from your geometry classes, if you have the sum of squares and then square root it, that is not the same as the sum of those of each of those base numbers. So it's going to be a little bit bigger. You can kind of think of Pythagoras with adding up squares and then square rooting. So this is what the formula is going to be. There's two little tweaks to this. Usually when I teach this, I reveal it at the end, but for the video, I'm going to try to go a little bit quicker here. So, but there's two tweaks. One is, like I said, instead of absolute valuing, we're going to be squaring. And then because we're squaring, I need to then get back to my data, to my correct units. So imagine that all my data values here are in inches. I'm measuring something in inches. Somebody's, I don't know, let's say feet. We're feet and we're throwing paper airplanes. So the furthest one went 7 feet. I guess that's not a very good paper airplane, but nor is one. But let's say they're feet. And at some point, if I square all these units, then they end up with feet squared. So I need to then put it back to then be my regular units of feet, and so we end up square rooting it. Be mindful of square versus square root. This is the square, and then this is the square root, which goes back, gets us back to the roots of what the square was. And then the other tweak is we're dividing by n minus 1. I'll talk about that in a minute, but that's another little tweak to the standard deviation. So two tweaks. One is we square, then we got to fix it by square rooting, and then n minus 1. If you were really insistent about finding this by hand, which don't be. In a minute, I'm going to show you how to do this by technology. Here I have 8 data values, and it's a little bit painful enough doing it with these 8. Imagine if you have lots of 8s that you needed to do, or you had 20-something, or 50, or 100, or 1,000. Good grief, no. We're going to want to use technology. So on here, if you did have to do it by hand, I'd encourage you to do it in a table like this. So here's x. I just list all my my data values out. So 1, 2, 2, 3, 5, 6, 6, 7, the same data sets we've been using this whole time. And then I'm going to find my deviations, which we found just a second ago here. I did it quickly without even showing the math, and most of you probably didn't even blink an eye. You're like, yep, I can subtract that from the mean. A little bit more formally, if I subtract each of them from 4, notice again that's why those are negatives, and that's why these are positives. So that's how that's our deviations. Notice if I add them all up, I get 0. Here's that what I said earlier. It's that capital Greek letter. This symbol. This means sum up, and it's capital sigma. It is important to note that it's capital, because in just a second in this very video, you're gonna learn about lowercase sigma. So capital sigma is sum up. It does look like an E, but actually really is the equivalent of our S, of our Latin letter S. So we're going to take our deviations, and then we're going to square our deviations. So each of these numbers, we're going to square. So if I take -3 square, I get 9. -2 square, I get 4. +4. Do note that these, I have parentheses written around them. If you didn't have the parentheses, just the math teacher in me, that would be a mistake, because that would be -3 squared is a negative times 3 times 3, or -1 times 3 times 3, which would be a -9. So if you do, for some reason, want to type -3 squared into the calculator, you must have parentheses around that -3 before you square it. So if I know this, I get 9, 4 and 4 again, -1 squared is 1, and then back up, 1 squared is 1, 2 squared is 4, 2 squared is 4, 3 squared is 9. So now these are my squared deviations. So same old, like we just did a second ago, let's find the average of these. So to find the average, I'm going to add them all up, 36, and then divide by n. As that other tweak. Instead of dividing by n, we're going to divide by n minus 1. I'll explain a little bit why-ish in a minute. So we're going to divide by n minus 1, which is 7. And then because we're squared, if these were feet, notice these are all feet. Foot minus feet is still feet. And then all of a sudden this is feet squared. So then when I divide feet squared by just a number, I still have feet, I forgot the square, I still have feet squared. So that's why I need to square root it to get it back to just feet. So this corrects our units. So notice I get 2.268, which is just a little bit bigger than this 2. It's a little bit bigger for two reasons. One, the whole square business. Square rooting is going to make it be a little bit bigger. And then the other is this divide by n minus 1. Now, what if we didn't square root? Then we have a name for this, and that is called the sample variance, or more specifically the variance. Oh, I forgot a second ago. We often, you'll see me abbreviate standard deviation as just SD or STDEV. It's probably not a good idea to just abbreviate standard deviation as STD. It's a little awkward, especially if you're training to be a nurse. SD or STDEV. I know like Excel uses the STDEV. So if you use, and then the abbreviation for variance is VAR, just VAR. So then if I take the sample standard deviation, and I'll explain the whole sample business in 1 second as well, but if I take my standard deviation and I square it, then that's how I can get my my variance. Or just simply don't square root it, so it's at 36/7, and we get this. I did write this as an about, because the decimal places were, it ended a few more out because it is dividing by 7. But these variances should always be fractions. There should always be possible to be written as a rational number. You might have decimals here or something like that, but as long as, well, I guess I take that back. As long as you have rational x's, then this variance should always be a fraction. If for some reason this was a square root of 2, then that wouldn't be the case. But usually, oftentimes, your variance can be written as a fraction. So, let's talk about formulas here. Why do we care about variance real fast? It's a little bit in the weeds, but the variance is actually mathematically a bit more accurate than our standard deviation, because this can kind of make it be a little bit messy. And mathematically, it's the thing that we get to first. This process here, where we are squaring things, if we were to cube it or raise it to the 4th power, those are this similar process, other things in mathematics. We call this the second moment. There's the third moment, the fourth moment. It's skewness and kurtosis, things like that. But what I'm getting at is mathematically, the variance is actually the thing that we arrive at first. And even more importantly, depending upon your stat class, I know like in my business stat class, we teach about there's a little rule called variances add when you're combining random variables. And so being familiar with getting things to the variance level, which is what we kind of get at first and be able to use and manipulate, is a familiar thing. So you need to understand that if I square the standard deviation to get the variance, and if I want to go backwards, I can square root. And I gotta have that summarized down here. So the formulas of the two things we just learned, the sample variance. And so here I'm talking specifically about, I have a big population out there, a big group of things that say all students at your college or university or high school, and you're going to take a sample, and maybe you want to see what's the you don't have access to contact the registrar, because you're just a student, but you want to find the average GPA of students in a certain group. Let's say of all students on your campus. So you go take a sample of everyone that you're able to, nice random sample. It's not the full population. Because we know that we're missing some people in the population, we're going to do a little bit of a fudge factor, a little bit of an estimation here, and that's what this n minus 1 takes care of for us. I'll show you the population formula, and then I'll compare the two in a second. But we're talking about a sample, a small group from your big population. So here's our formula. So let's look at what we did up here. This 36 was the sum of all of my sum of all my deviations squared. So I find each deviation, square it, and then add them all up, and that's at 36, and that's what this numerator is here. And then all I have here is then if I can square root it, or divide by n minus 1. So that part should be more straightforward, but that sometimes throws some people. Notice if I have the variance, I need the standard deviation, square root. This is going to be true throughout your statistical education experience, whether it's this class or other future classes, that's going to always be true. Square root it to get the standard deviation. And then to go for, if you have the standard deviation, you need the variance, you square it, always and forever. It's just this relationship here. Do notice that when we're square rooting, we don't have to worry about pluses or minuses or anything like that, because measures of spread, measures of variability, will always be positive. Your range, your IQR, these are measurements of width. If I was to measure a table, I wouldn't say that this table, is 2 feet, negative 2 feet wide. That'd be weird. So their measurements of spread are like measurements of width. They're always positive. They're those distances. So you don't have to worry about pluses or minuses. They're always going to be positive. So now let's talk about the population variance. So suppose that you had access to grab every individual in the population, whether it might just be these eight things, or whatever. You're able to contact every student at your school. Maybe you were just curious about the students in your stat class. That was your population. So you sampled everybody. You've gathered information from everyone in your stat class. Then we're just going to divide by n instead of n minus 1. That's the difference. That's the main difference. There's a little bit of symbol change, but this S or this symbol, they both mean standard deviation. This X bar or this symbol, they both mean mean. But the big deal here is that we're just dividing by n instead of n minus 1. So think about, let me backtrack just a little bit by looking, not backtrack, but just look at our numbers here. So here our sample size was 8, so I divided by 7. So imagine that there's a big population. Imagine your school, probably pretty big. And with your school, my students, by the way, I'm talking just in general in case anybody comes across this. I know at Temple College, I know the size of our school. But imagine your school, lots of students there, probably in the thousands or so. If I just grabbed 8 individuals from this population, especially if for some reason it was negative numbers was available, maybe this was rounding to the nearest hundreds, how many dollars are in your bank account. Somebody might have a negative, they've overdrafted and they have negative numbers. So if I was to take this sample, it's possible, likely even, that somebody has more than $700 in their bank account. So I don't know that much about the population, so I'm going to need to kind of estimate, kind of fudge out. I like to think of it as the Thanksgiving let out. You just had Thanksgiving dinner, and your belly's so full, and you just undo your belt, and it just kind of opens up just a little bit. Because imagine instead of sampling 8 people, the amount of uncertainty with 8 people, that's a good bit of uncertainty. I only asked 8 people about this, but imagine if you sampled 80 or 800. If you sampled 80 people, you know a lot more about the population than you did before when it was just 8. And so think about the difference between 80 and 79. Well, to do that, let's just think about a pie. So let's imagine that someone's really cold cheesecake and they cut one cheesecake into 8 slices and another into 7. You'd be able to tell the difference between those 2 slices. You'd be like, oh, that one's bigger, I'm going to want that one. But if someone with a really cold cheesecake and a very sharp knife manages to cut the cheesecake perfectly into 80 slices, and then they cut another cheesecake perfectly into 79 slices, even slices, and they put an 80th and a 79th on a plate right in front of you, you probably wouldn't be able to tell the difference between the two, though there is a difference. And that just goes to show that as we know more about the population, the difference between the sample statistics, the variance and the standard deviation, are going to be getting closer and a lot more negligible. That -1 starts having a smaller and smaller effect. That's what I see down here. The sample standard deviation and the population standard deviation. The sample standard deviation should always be bigger than the population. Same thing with the variance. But as n grows, they're going to get closer together. Just logically, think about that. It's because we know more about the population. Lastly, in case you aren't familiar with these symbols, let's talk about these symbols. I think in my current stats class, this is the book goes into detail about this here. In my business stats class, I think This doesn't show up kind of until like chapter 8-ish or so, dealing with the difference in population and sample, but it's good to know. So this symbol, this is a lowercase sigma. The capital sigma was the sum up symbol. This lowercase sigma is the lowercase sigma. I draw it like this. I'll draw a little loop and then flat top. So I'll draw a little O and then flat, little O and then flat. That's how I draw it. Sometimes it gets really long, but that's how I do it. Some people will just draw it like they would a 6, but they just do it kind of flat, like this. That's a little bit weird to me. I like to do it that way. Either way works. That's lowercase sigma. And then the mu should be familiar because it's right below my face in our Simpson Math logo. That mu is deliberately, that M in our Simpson Math logo is deliberately a mu. And the S, by the way, is deliberately from calculus an integral. So that is just a mu. So you don't draw it this way, but imagine if you were to draw a lowercase u and then put a tail on that left-hand side. That's what the mu should look like. But when you draw it, you usually just start on that bottom left corner and just draw it like that. All right, so that's mu. Yes, mu, mu2. It's a whole thing in stats. I make pins, as you know, some of you know. I plan to make a mu and mu2, but have it look like that symbol at some point. Shh, don't tell anyone. Okay. So I think that's that. So that's the gist about standard deviation. What I want you to know, let me just wrap up before I start talking about technology, is that if you think about what I did at the beginning, where if you think about a measurement of spread that's the average distance the values are away from the mean, great. It's technically not the average, but it's that idea. It's the average with a little bit of messiness in there. So instead of the average, it's the typical distance that the values are away from the mean. Basically an average. It's technically just slightly bigger than the actual average, but basically the average distance the values are away from the mean. All right. So I'm going to first show you, I'm going to show you on Desmos just because I have it up, it's going to be quicker. So let me show you how to do this data set on Desmos. I already have this up. I'm going to delete it and then redo it. Can't I make it bigger? Yeah. We don't need the graphs over here. I just need this space above my head. So let me just show it to you, and then I'm going to show you how I type it in. I'll delete it and redo it. So I have my list typed in. Notice it is typed in with a letter, can be uppercase or lowercase, but it needs to be one single letter, and it is case sensitive. Equal to, square bracket, and then you type in your list. The reason why you don't have to do this way, you could just type in this blank 1, 2, 2, 3, 5, 6, 6, 7. But if you're going to use this list several times for several summary statistics, it's a lot faster just to type A instead of typing this over and over and over. Also, a lot of things like I know some students that use MyLab or Excel. If you just copy it, if you have your list and copy and paste it, it should probably auto paste it in correctly. So that's also a nice thing. I will have a video where I'll showcase many summary statistics later. I'm just showing off standard deviation today. And then here are the formulas for the sample standard deviation and variance, and then the population standard deviation and variance. Notice the difference between the population and the samples. The population has an extra P tacked on. So it's VARP or standard, but it's that P for population. Whenever there is a way to show these functions in statistics, so I open up my keyboard, the on-screen keyboard, and selected functions, scroll down to statistics, and you'll see STDEV, standard deviation P, that's the population standard deviation, and the variance. They don't show the variance P, they don't show a VARP, but it does exist. As you see, I'm using it here. So you can just type it in, but you won't be able to shortcut it. Just type it in, VARP, or grab the var and then add the P. All right, so I'm going to kind of undo and just do this kind of from scratch. So if that explanation was good, you can skip ahead, or let me just show you this from scratch. So I have a clean one. I'm going to type in my data set. I'm going to pick any letter. A is just easy because it's the beginning of the alphabet. And then equal sign. If you do it on screen like on your phone, then you can just grab a letter. I would not probably do X or Y because that's going to start doing graphing things. So then you can, like I said, grab A and then click equals. and then you'll need to do your square bracket. So if you just click on the square bracket or on your keyboard, it's Shift and it's the brackety thing next to the P. Notice that Desmos will help you out by auto closing the bracket. It gives you a little ghosted bracket. It doesn't want you to not include the bracket, so it's forcing you to have that. If you don't do anything, it'll auto close it later, or you could type it closed. So I'm going to do 1 and then comma, and I'm just using my keyboard, or you can use a screen, 2 and then comma, and then keep going. You do need to include both 2's, because both of those 2's are in the data set. If you didn't have that, then you would not have the correct standard deviation. Desmos will then tell you how many elements are in that list, which is just helpful for if you know that there's supposed to be 8 and you realize you just have 7 for some reason, maybe you missed a comma. If you had multi-digit words, multi-digit numbers, and you knew there was supposed to be 8 and you had 9, well, you might have an extra comma somewhere. Go through and find it. All right, so then you can type in STDEV. Notice what happens for the standard deviation, STDEV. When I'm typing these letters in, these are italicized, and the Desmos is saying, oh, do you want to do sliders? E, by the way, is like a number, so that's why it's not asking about E. But it's italicized. Desmos doesn't know what that is. But notice the moment I press the V, it snaps to being regular font text, and that's Desmos saying, I know what that is. That's one of the functions that I know what it is. So then you need to then do an open parenthesis, and then put in your list, in this case A. If you're not sure, this little triangle will pop up, and it can tell you like it needs more arguments, so it needs multiple numbers. So it's like try putting in 1, 2. In this case, we have a few more than 1, 2. If you didn't just want to type it in from scratch, you can open up the functions, scroll down to statistics, just click STDEV, and then say A, or come over to ABC and then say A. I'm going to go a little bit faster on these others. So that for the variance, you can just do var, or scroll down and click var of A, and there's the variance. You also, just to prove the point, if I take the standard deviation, and I'm cheating, I'm just going to copy and paste, took standard deviation of A and squared it. Notice if I square this, I literally get the same thing that I got before. So if you already had the standard deviation, you could just square it to find the variance. How did I do the square on my keyboard? I did Shift 6, and now I'm in the exponent, and then I added the 2. On the on-screen keyboard, you can just click this to give you the square, or you can just click the A to the B to get into the exponent, and then type in a 2. One more thing, another thing about Desmos is that with this, if you want to force it to a fraction, like I said, the variance should be a fraction, so that's nice. Another little trick with Desmos is, let's say you did some calculations like with the standard deviation, and you want that to be named just S. So I can shorthand call this S, and then again, I can just say S squared. And so here I'm saying standard deviation is S, so wherever else I use S, it's going to look back and grab what S equals. So now it's taking that S and squaring it and getting that same variance. So that's another option there. All right, and then quickly, the standard deviation of the population, so it's the STDEVP of A, and then I just have to key this one in, VARP of A, and the of, I'm saying of like it's parenthesis, like it's a function, because that's what really these are. These are known functions. So the variance function is running through all those functional calculations based upon this specific input. All right, so that's how you can get the standard deviations and variances, both sample and population, on Desmos. All right, I'm going to show off the 84. Please turn back on. There we go. Okay. So with this, I already have it ran, so you can see here I get my sample standard deviations, the 2.626778, and the population standard deviation, 2.121. So I'm going to backtrack and show you how I typed this in. I did this. The short answer is I did stats, calculate, 1 var stats. Here var is not short for variance, it's short for variable, 1 variable statistics. And then also, if you needed to get this these numbers squared, You could just write these down on your paper and then type them in and square them so to get the variance, or I'll show you a shortcut. But first, let me show you how we put this into the calculator. So I'm going to quit out of this, press Stat, Edit, and here I have my data already typed into L1. I'm going to clear it, so if for some reason there's something here you don't want, make sure to press Clear. If you press Delete, it will delete the list. Let me show you what would happen if I press Delete. L1 is gone. It is gone. It is not here anymore. You could just call it quits and press second plus 712. That resets the calculator and it will show back up empty. Second plus 712. Second plus 7 1, and that 2 would actually do it, but I don't want to do it. So I'm going to show you how to fix it if you don't want to. So L2, I'm going to arrow up and press second insert. So second delete, which is insert, and then it's saying, okay, what do you want to call this list? And I want it to be L1. So second one or L1, and it still remembered the list. So it didn't actually forget the list, it just deleted it off of this view. So I'm going to press clear so that way it goes away. And now I'm going to type in the numbers. I'm using my keyboard on my computer because it'll be a little bit faster. So 1 and press enter. So 2, enter, 2, enter, 3, enter, no 4, 5, 6, 6, 7. All right, so I have my numbers, which is a good tip. Again, just like you're counting the elements, I've arrowed up to the last one, and I'm looking, it says L1, 8. That's saying it's the row 8. Or the 8th entry, so that way I know I'm supposed to have 8 numbers. I typed in 8 numbers. It's, not a foolproof way, but it is a way to check for a little bit of errors. So now press second mode or second quit, and then stat. I want to go to calculate, so right arrow, and just pick this first option, 1 var stat or 1 variable stat. All right. By default, it should just default to L1 and it should already be there. For some reason you typed your data into L2 or L3, then you could say second 2 or second 3 or wherever it is. If you had a frequency list, which in our data set we could have, it just would have taken us longer. I could have typed in 1, 2, 3, maybe even the 4, 5, 6, 7. And then next to the 1 I would say 1, and the L2 I would say 1, and L2 next to the 2, I would say 2 because we have 2 of them. 3, next to the 3, I would say 1. Next to the 4, I would say 0 because we got none of those. 1, 5, 2 6s, 1, 7. So you had a frequency list like that, which probably you won't see something like that within our courses, but you might. Then you would tell the calculator, here's my frequency list is here. But you can just leave it blank and then say calculate. So the mean is 4 like we knew it would. We're just needing these two, but let me show you what the others are real fast. So this, at least just these other right here. The others down below are 5-number summary, which I'll go through in another video. But this right here, so this is the sum of all the x's. So if you wanted to fake the mean, if you needed to show the work for the mean, this is the sum, this would be the numerator of the mean, divide by 8, gives you that 4. So you're going to always take the sum of my x's, divide by 8 to get that 4, to get that mean. This is sum of the sum of the x's squared, not very helpful in our case. Does this one? No. In the Inspire, if you have an Inspire and you do this, the bottom line, it does put out the numerator of the standard deviation. It does the sum of the deviation squared. So that's kind of nice. All right, so here's my standard deviation and variance. Now, how could I go about squaring them? Well, I'm going to hit quit. I could type in, and I'm looking over here, I'm cheating. So let's say I wrote it down, and I'm going to type in 2.26778683.806. I could take that and then square it, and do that and get a pretty good estimate of my variance. But there's a better way to do it. So if you press bars, this is not short for variances. This is short for variables. Vars, and then go down to statistics. These are my statistical variables. A lot of statistical variables were just done and saved. So they're not so much variables, but they do change each time you do a calculation. So if you see this SX, that is what we just found, which was this 2.26 or 2.27. So if I just select it and press enter, there's that standard deviation exactly. So this number and all of its decimal places, does it have more decimal places? Maybe it's just those. But this number and as many decimal places as it was calculated is stored in this SX. So if you have this XX, oh, I'm getting that by just highlighting it, going up and pressing enter, and it copies and pastes it down. And then I square it, that gives me my standard deviation for my sample. To the my sample variance. Now I want my population variance. So there's my population standard deviation. I'm going to press enter just to double check. Yep, that's what that was. I'm going to grab that back and now square it. And there's my population standard deviation of 4 points. I did it again. There's my population variance. This is variance. This is standard deviation. This is variance. This is standard deviation. Okay. Now let's move. I hope that helps. I'm going to move on to Excel. All right, so here's, you can just kind of screenshot this if you're familiar with Excel. I have my list here. I did do, and I'll explain this in a second, but I did do in my variance, my standard deviation formulas, I just did the whole column because if you look at the help on this, if you click on this, it'll pop up the help. And it says that it ignores logical values and texts in the sample. So if I just say, hey, find the standard deviation of this entire column, it's going to see, oh, well, this is the word list. I can't find the standard deviation of a word, so it just ignores it. It just skips over it. And so it just looks at these. What's nice about this is, let's say someone rushes in, oh, I found a ninth data value, and so I go, oh, great. What is it? It's 12. I type in the 12. All these automatically update because it's looking at the entire list, not just these cells, but it's looking at this entire column. So that's handy. So especially if you get a new list, you can just copy and paste, and you don't have to worry about adjusting what this is looking at because it's looking at the whole column. All right, so I'm going to go through this. I'm probably not going to, I might do a few from scratch over here, but all right, so you can copy or type these in, just pick a list, type it in. Here I have just a word list. If it was, I don't know, feet thrown, that could work too, whatever. I have my S squared, sigma squared. It was a little bit fancy, and I found the actual square character and the actual sigma here. To be able to do that on a Windows computer, it's really easy. Just press the Windows key and then period, and then up pops a bunch of emojis and the and then the comojis, and then here then just some symbols. So under the infinity of the symbol, that's where you can find the square, and then under this last one are the Greek letters, and you can find sigma under that list. So you just click and add them in, or you can just write sigma. What I usually do is sigma caret 2 to say sigma squared, and that works. This is really just for you, whatever this works for you. All right, so this over here, just FYI, this is just a thing to print the formula that's beside it. That's all this is. It's just printing the formula here. All right, so the standard deviation. If I want to find the standard deviation, let me scooch these over. So I'm going to say equal to, and then STD, and that's pretty much, even ST kind of works, but STD kind of narrows it down for us. And these are the two main ones that you're going to be using. There are these, they've been discontinued, don't use them. So there's stdev.p and stdev.s. You can read what the help says, but probably logically, P is for population, S is for sample. So for S, the standard deviation, it would be the standard deviation of S. You can click. If I have my hands on the keyboard, the best thing to do is to press Tab, and it will take it and it will put the open parenthesis right there beside it. So use that, and I could just highlight from A2 to A9, but as I said earlier, it's kind of nice just to say all of A. So I just clicked from A, and it says it's going from A to A because if I did this, it would do from A to B, so it has that option, but I just want A. And then I'm going to press enter to close. It'll auto close the parentheses because it's not too complicated. Sometimes if you do complicated formulas and you don't close the parentheses, it gets mad at you. So that's that one. Then there is a variance formula, so I can just say equal to, and you remember the equal starts the function. So equal to var, and then we're going to do var s. You can also double click if you have a mouse, and then do your click on A to get A to A. I might not need to do the variance squared, sorry, the variance thing, because I could just square my standard deviation. So I'm going to just say equal to this number, and then caret 2 to square it. You also, by the way, for the standard deviation, you could say equal to this number, and then square root it. So you could do to the 1/2 power. That's one option. Or you could say equal to SQRT, that's shorthand for square root, equal to the square root of the variance, if you found that. So notice, again, they're the square and square roots of each other. And then the standard deviation P, so STD, and grab the P, tab, click in the A, done, and then equal var, but this time the P, tab, click, done. And again, you could square it, so I could just take this number, and that's a $, and square it. That's it. In another video, I'm going to show how to do these things, how to do like mini summary statistics using Desmos Excel in the 84. But I just wanted to kind of feature the standard deviation because those are a little bit more nuanced. So hope this helped you understand what standard deviation is a little bit better. It is the typical distance, basically the average distance, but it's the typical distance of values are away from the mean, and these various ways that you can find the standard deviation using technology. Please, for the love, if you're in my class, do not, after today, after you first kind of maybe learn a little bit, do not just keep finding the standard deviation by hand. That is obnoxious and annoying. Use technology. Seriously, don't. We have technology for a reason. It is more important for you to understand what standard deviation is than be able to just keep calculating it by hand. That's ridiculous. All right. Soapbox over. Where's the end button? All right. You'll have a wonderful day. And make sure to see me in the next video where I talk about finding all these calculations. All right. Take care. See you in the next one.